Hello, welcome to another episode of Naked Neuroscience, the podcast exploring the workings of the brain and the nervous system in our bodies and beyond. I'm Katie Haylor, and this month
we now have two types of addictive behaviour which have quite different underlying brain mechanisms. So we should not think that addictive behaviour is just a unitary phenomenon.
we're delving into the addicted brain, asking what is addiction, who's vulnerable to developing addictions, and what's actually going on in the brain. Plus, we're stepping into some other neuroscience news stories with the help of our local experts. Let's tuck into some neuroscience news with Helen Keyes and Duncan Astle. First up, might the anti-vax movement be gaining traction at the moment because A comes before V? Well, a paper published in the Journal of Consumer Psychology suggests that tapping into the patterns our brains are familiar with makes us more likely to believe something. Anglia Ruskin University psychologist Helen Keyes, who wasn't involved in the study, took me through the findings.
Our brains love to search for patterns and we love to be very efficient. And in that way, if something falls into a pattern that our brain recognises or likes, it believes that it's attracted to something that fits into a normal pattern for it. So it's an efficient way of processing information. That's what I mean by being a cognitive miser.
Okay, the brain likes patterns. Got it.
The brain likes patterns, and there are some patterns or sequences that are so well learned that we might call them natural sequences. So things like numbers, 1, 2, 3, 4, 5, or indeed the alphabet, which is what this paper focuses on. So we're more susceptible to believing a message, any sort of message, if it's repeated. So that's one key way of getting people to believe you. But also if there's a perceptual fluency, if it's easy for your brain to process something, you're more likely to believe it. So this study wanted to know that if perceptual fluency is so important to us, will statements that conform to some sort of natural sequence be more believable? And the natural sequence this paper focused on was the alphabet. They asked 172 participants how much they believed in a particular statement, and they made subtle changes based on the alphabet. So they might ask a participant how much they believed a statement such as androgel increases testosterone. So the letter A comes before the letter T in the alphabet. Androgel increases testosterone. Compared to a statement very similar, which would be undrogel increases testosterone. So here the letter U does not come before the letter T in the alphabet. It's not following that natural sequence.
I see. Okay.
So they found surprisingly really clear results. They matched these words for how much these words were liked and how much they seemed like brand names. So there was a lot of things controlled for here. And they found very consistently that people preferred statements where the first word began with a letter earlier in the alphabet and the second word began with a letter from later in the alphabet. What surprised me was they did a second experiment that showed if they primed people by playing the alphabet backwards prior to this experiment, the effect could be reversed so that you would demonstrate a preference for undrogel increases testosterone instead of androgel increases testosterone. I found that a bit strange because the natural sequence of letters is so ingrained and so overlearned in our brain that that was quite a surprising result for a cognitive psychologist, but they do show that it has this immediate priming effect. So really what they're saying is that the brain stores these natural sequences, and when it finds a natural sequence, so A coming before B, A causes B, the brain feels at ease and it's much more susceptible to liking that statement and believing it as true.
It sounds like rhetoric is what you're talking about. Are we talking about politicians making speeches, advertising campaigns, the idea of rhetoric and using this potentially to reinforce messages?
We absolutely are. So this paper was coming at it from a marketing perspective, so everything you're saying there, but it does equally apply. If we're looking at politics, we can use this in a positive way. If we're looking to nudge a population towards particular behaviours, so if we're looking at health claims, perhaps this would be a better way to get a message across. A causes B rather than C causes B or B is caused by A. There's clearer ways to get messages across. And they say there may be implications as well for even for things like jury duty. So A killed B is more believable than B killed A, for example. So there's more to explore here around how we construct statements and how they can be used to good or nefarious effect.
I find this a bit unnerving because I like to think that I'm quite critical when it comes to statements that are claimed to be true or not true. Do you think perhaps we all just need to be a little bit more critical when it comes to the messages that we're receiving?
Well, I couldn't agree with you more. And I think this is going to be a subtle effect. I think if you read a headline that said something outrageous, A causes B, it's not taking away all of your critical capacity. But when we do skim over things and when we're very distracted by things and a headline grabs our attention, it is suggesting our brain just likes things that are easy, that fit with patterns that we're very familiar with. That makes a lot of sense to us, really. We tend to believe things that fit with our own patterns of thoughts anyway.
So how are you going to change your behaviour not to fall into this trap? Have you got any advice?
I'm just going to read the full article.
Helen Keyes from Anglia Ruskin. Now to cognitive neuroscientist Duncan Astle, who has this month been looking at another stimulating paper. Last month it was around depression, and this month, memory.
Do you know what the secret to great comedy is? Timing.
You beat me to it. You beat me to it.
Actually, it's really important for all types of communication, is timing, and that's true of the human brain as well. And so we know that rhythmic electrical activity in the brain is a really important way in which different groups of neurons synchronize and speak to each other. So if you have a very small network with just a few neurons, that has a rhythm that's very rapid. And that's because there are fewer neurons in it and the gaps between the synapses are shorter. If you have a very large network, then the overall rhythm is much slower. And this is really important because what these larger networks with slow rhythms can do can act a bit like a conductor in an orchestra. So if you had two different groups of neurons that are small and far away from each other and they have a rapid rhythm, what they can do is synchronize themselves with the slower long-range brain network, and that rhythm can then act like a coordinator or a conductor that helps them work together. And we know that's a really important feature of how brain activity is organized in the human brain.
Okay, so what's this got to do with the paper that you're going to tell us about?
What they did is they attached electrodes to people's heads so that they could look at this kind of rhythmic coordination. And what they showed is that in much older adults, so adults over 65, there was a reduction in the coupling that you get between these different frequencies in parts of the frontal lobe towards the front of your head and parts of the temporal lobe towards the side of your head. And that this drop in coupling that they observed mirrored a drop in short-term memory performance in these older adults.
Is the inference then that this coordination, this orchestration is important for short-term memory? Do we know that to be the case?
Well, people have made that claim before, but what this paper does next is really nice in showing the causal relationship between those two things. Because what they then did is attach different types of electrodes to people's head and then passed a type of electrical current through their brains, which is called transcranial alternating current stimulation. And what they did is they tuned the frequency of the stimulation coming from these electrodes to the normal frequency of each person's slow kind of conductor rhythm. And then they essentially stimulated them for 10 blocks of trials whilst they performed this short-term memory task. And what they found is that subjects' performance improved markedly during this stimulation relative to a control condition. And this improvement continued even once the stimulation was turned off. And then when they looked at the brain oscillations, they saw that not only was performance improved, but this kind of rhythmic coupling was also improved by the stimulation. So that implies that there is some causal relationship between the strength of this rhythmic coupling and people's short-term memory abilities.
Could this be used in a situation where you're trying to help somebody with their short-term memory? Perhaps it's age-related.
Exactly. So we're all getting older, and those of us who are over 60 plus might start to experience difficulties in areas like short-term memory. And as a society, we're always looking for new interventions, and people often think immediately of pharmacological interventions. But the exciting thing here is that if we can build a proper evidence base surrounding what this kind of stimulation does to the brain and how it works and what the benefits are, then in the long run, we might be able to move to interventions that aren't just pharmacologically based, but that are also based on things like brain stimulation.
You talked about a stimulation type technique last time, actually, on last episode, I think. And I asked you a similar question, which was, how long does this effect last?
There are various different schools of thought. So last time we talked about transcranial magnetic stimulation, which, depending upon how you do it, has a relatively short after period. This transcranial alternating current stimulation is a little bit different to that. But again, people tend to think that it has a relatively short after period. But the idea is that regular sessions or regular treatments with it might be able to result in a sustained change.
Duncan Astle. And if there's some neuroscience news you want us to look at, or you've got a question you'd like us to address, get in touch. You can email neuroscience@nakedscientist.com. Maria got in touch to ask where to find references to the news items we're discussing. They're listed on the news subsection of each episode's show page on the Naked Scientist website. If you go to nakedscientist.com/neuroscience, you'll find all of the episodes listed.
Hello, I'm Chris Barrow, bringing you a brand new podcast called Naked Gaming. This is where we look at gaming news.
If you have a hit, if you make a first game and it hits, it's incredibly hard to recreate that in the second game.
Reviews. Is it wrong to give a game 0 out of 10? That feels...
Oh, I love it. Go for it.
Okay, I'm just going to go hard in here. 0 out of 10. Don't waste your money. And we also go back in time with Retro Revival.
I think I'm a hypocrite because last time I'm like, oh, well, they just made the same game again and that's bad. But this time I'm like, nah, it's pretty good. I'm happy with that.
Make the same game.
Make it again.
Download it now wherever you get your podcasts.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions. And this month on Naked Neuroscience, we are analysing addiction. So to find out what addiction is, let's journey back to July 2018, when on the Naked Scientist show, I, alongside Chris Smith, spoke to Cambridge University's Amy Milton about exactly this.
So addiction, we normally think about in the context of drugs of abuse. In addiction, behaviour narrows very, very markedly to being really focused on drug-seeking and drug-taking behaviour. And that's to the exclusion of everything else. So people losing their jobs, their family, and so on. And the key characteristic of addiction is that there is a loss of control over that behaviour. So people are aware of the fact that these behaviours are hurting them, but they can't do anything to stop doing it. And it's a chronic and relapsing disorder. So people will often manage to get off drugs for a period of time, but then they're very at high risk of relapse for the rest of their lives, actually.
And do we know how addictions work in the brain?
We have a pretty good idea. As you can imagine, for a complex mental health disorder, there are lots of things that go wrong. There are a few key things, though. So one is that drugs of abuse massively increase the amount of dopamine within the brain. And dopamine is a really, really key chemical for learning about things that are motivationally relevant to you in your environment. So we normally learn about rewards, natural rewards like food and mates and so on, with big increases in dopamine. Drugs of abuse increase dopamine massively more than natural rewards, so hundreds of times more. What this means is that the behaviours that lead to the drugs being obtained are far more likely to be engaged in. There is a shift very, very quickly, because dopamine encourages this, from goal-directed behaviour, doing something because you want the outcome, to habitual behaviour, where we just do it because that's what we do in a particular environment. Dopamine increases the influence that the environment has over behaviour. So cues in the environment that are predictive of drug rewards come to be far more attention-grabbing and controlling of behaviour. And the key clincher is that there is a loss of cognitive control mechanisms mediated by this area called the prefrontal cortex. Many drugs of abuse are very toxic to the prefrontal cortex. And people who tend to become addicted often have lower inhibitory control to start with, and the drugs of abuse reduce that inhibitory control further. So that habit becomes a compulsive habit.
Can anything be addictive?
It's a really good question. With drugs of abuse, it's very, very clear that there's something unnatural in the body and that drugs of abuse hijack our natural reward system. When you've got a natural reward, so something like high-fat, high-sugar foods have been suggested as potentially addictive, gambling, other sort of potentially behavioural addictions, it's often harder to tell whether that's a hijacking of a natural reward system or is just the natural reward system itself. So sex addiction or food addiction is much, much harder to quantify. And it really comes down to, is the behaviour having really adverse outcomes on the person who's engaging in them?
So if someone's addicted to something, what happens if they don't get their fix?
So they go into withdrawal, but there are at least two different types of withdrawal, physiological and psychological. Physiological withdrawal, it's really obvious withdrawal signs. So if somebody stops using heroin, for example, when they've been using for a long time, they will show a particular set of symptoms like getting a really bad dose of flu. They often get quite bad diarrhea, all these very physical symptoms that are quite clearly there. What you get with psychological withdrawal is the system has been massively overstimulated for a really long period of time. So the reward system has gotten used to being active at a certain level. When a system like that is overstimulated, it becomes less sensitive. It's like the cells that are receiving the signal kind of put their hands over their ears. They're no longer listening unless they're being shouted at. So you take that drug away and you go back to normal physiological levels of stimulation. Those cells that are receiving the signal aren't listening anymore. And so you get a rebound effect where people feel very depressed. They often feel very anxious. And the way of getting out of that state is by going and engaging in those drug-seeking and drug-taking behaviours again.
It was made as a joke at the Edinburgh Festival by a comedian, but it sort of has a serious side to it, which is this person said, why don't you just take hundreds of drugs because then your body won't know what to get addicted to? But how do you, or how does your brain make the association between a particular drug and you know you're hooked on it?
All drugs of abuse, even though they all have very different actions in the brain, so nicotine, very different from heroin, very different from cocaine, all of them have this common action of increasing dopamine in a particular part of the brain called the nucleus accumbens. And every single drug of abuse that is addictive has that effect. And you are very, very good at learning in a completely unconscious way which environmental cues predict which particular outcomes. And you can see variation. There are even experiments in rats showing that if you have rats who can self-administer cocaine or heroin in different environments, they tend to take heroin when they're in their home environment and they tend to take cocaine when they're out in a novel environment. So these environments really influence drug-seeking and drug-taking behaviour as well in quite a complicated way.
For someone who does have an addiction, what kind of treatments are there?
So we are very limited in the treatments that we have at the moment. There are treatments that exist like the 12-step program, which don't necessarily have a very strong scientific understanding, but if they work for certain people, then they should use them. But for other drugs of abuse like cocaine, there are no approved treatments. For other drugs like nicotine or heroin, we're looking at replacement therapy really as the alternative. For drugs like alcohol, there's antabuse, but quite often people will stop using antabuse, which produces hangover-like symptoms rapidly when somebody drinks alcohol. What tends to happen is people will stop using the antabuse and will carry on using the alcohol. So there's a real clinical treatment need and a real push for new treatment development, which is one of the things that my lab and other labs here in Cambridge are doing.
Amy Milton from Cambridge University. But why do some people get addicted to drugs and others not?
What neuroscience research tells us is that the processes that underlie your potential to try a substance are actually quite distinct from those that underlie getting addicted to something.
That's Cambridge University neuroscientist Camilla Nord, who told me briefly about the work of another colleague, Karen Ersch.
And she tested the first-degree relatives, so that's like sister, brother, parent, or child, of people with drug addictions. And she found that they all showed this heightened impulsivity, which is a behavioral trait that means you're likely to make decisions hastily, not think things through, maybe things that would be better to pause before you make that particular decision. And they all sort of showed this trait. But what was different about the people who'd actually gone on to develop an addiction, not just their relatives, were that they also showed showed this trait called sensation seeking. You really are going after those things that are fun. What she showed is that you need a combination of these two behavioral traits, impulsivity and sensation seeking, to show a propensity or maybe a likelihood of developing a drug addiction.
Right, so that could be the difference between smoking a cigarette behind the bike sheds when you're 13 and going on to become a chain smoker as an adult. Or taking illegal drugs less frequently compared to those who develop a dependence. Back in February 2019, Camilla published a study shining light on this question of who gets addicted to drugs. Specifically, it looked at impulsivity. But there are a whole host of other factors that could potentially contribute to someone's risk for developing an addiction, and the risk profile might vary between individuals.
For some people, their high impulsivity and high sensation seeking might be all it takes for them to develop a drug addiction. But for other people, perhaps they need those traits in combination with other kinds of more social or environmental factors. So I think the risks vary between people because it's so complex.
Camilla wanted to see if there are any neural markers or indicators in the brain predicting those who might be more likely to develop an addiction later in life.
So the only time you can really look at this is in adolescence, before they've been exposed to any kind of substance. So that's what we did. We took 99 young people with no history of substance abuse and put them in a brain scanner. There's a potential for early intervention if we find an early marker before the initiation of any kind of substance abuse. The second reason is a more scientific one. In the past, when you put people with a drug addiction in a brain scanner, you can't really disentangle, is that particular effect on the brain because they've been taking a drug for decades, or is it because they have some kind of underlying brain difference that might make them predisposed to take drugs? Who knows? But if you take adolescents who haven't yet developed any kind of substance addiction, we can find out what are those underlying mechanisms without dealing with the effects of a drug.
The team scanned 99 youngsters using an MRI scanner to image how much myelin was in their brain cells. Myelin's a fatty protein layer that forms around nerves and facilitates fast electrical communication. They zoomed in on a brain area with this MRI scan called the putamen. Camilla explained that addiction studies in animals have shown the putamen behaves differently in those who are more likely to go on to become addicts. And they actually used the same kind of behavioural task with these teens that they put in the scanner as with the rodents in previous work.
So in rodents, you can measure how impulsive a particular rodent is by whether they're likely to poke their nose into a little box before they know which box to poke their nose into. So they're trained that once a light flashes, they poke their nose in that box, they get a reward, they get a treat usually. But if they do this poke preemptively, before they've even been told where to poke, then they get no reward. It's maladaptive, and that's considered an impulsive response. So in our experiment, we used a human version of this task where humans have to sort of resist pressing a particular box before they know which box to press. But it's actually quite tempting to release what you're holding preemptively to go to press the box in anticipation of getting some extra points on the task. And this is our behavioral measure of impulsivity in humans.
While we couldn't replicate this exact experiment, I was curious to know how I might fare on an impulsivity test, so Camilla obliged.
I've brought you one of the most classic tests of impulsivity, and this task has to do with a form of decision-making impulsivity, which is maybe a little bit different than the form of behavior impulsivity I was telling you about.
I was tasked with deciding, do I want a small amount of money now or a larger amount of money later? Simple enough.
Would I prefer £54 today or 55 in 117 days? I'm going to have to go with today. Would I prefer £55 today or 75 in 61 days? Okay, so that's a couple of months. No, I'm going to go for £55 today. Would you prefer £19 today or 25 in 53 days? Again, I'm going to go for 19. And lastly, would I prefer £31 today or 85 in 7 days? Okay, 7 days is only a week, so I'm going to go for 7 days. Now, I've only done a couple of questions, but I feel like I'm quite impulsive.
What we can do with your answers there is essentially fit you to a curve. At which point will you choose the future rewards versus the present rewards. And yes, probably from your first couple questions, you would seem a little bit impulsive, but it's not always good to wait for rewards. It's not always good to wait 2 years for 1 more pound in these particular questions. So there's a benefit to being a bit impulsive. In fact, like most traits, there's a reason we've all evolved to have them. But there are, of course, disadvantages to being very impulsive in that it might actually be a good thing to wait a month for an extra £20. And we tend to see it relates to other kinds of impulsivity as well.
Okay, enough indulging in my own habits, back to the study.
We found that the kids who were most impulsive showed lower levels of myelination in the putamen. And the reason why this is exciting is because none of them have ever had a substance addiction, but they have this trait that makes them potentially predisposed to developing a substance addiction in the future. And they already show a neural difference that maybe is predictive of developing a substance addiction, but we won't know that until much longer-term studies are carried out.
So what does all of this mean for youngsters who might be at risk of developing a substance addiction later in life? I asked Camilla to put the pieces of this puzzle together.
I think less myelination in the brain relates to impulsivity could mean a lot of different things. And one could be a causal link between this neural correlate and future development of a disorder, but we don't know that yet. I think there is probably a causal link between behavioral impulsivity and development of a disorder, because we see that very strongly in animal studies. So animals who perform like this with greater impulsivity on the same task, they're the ones who get much more addicted to cocaine in animal studies of drug addiction than the other animals. So I think we can say that causal link with a little bit more certainty than the causal link between myelination and impulsivity. I think of it more as they're both manifestations of the current state of that person. One is in the behavior and one is in the brain, but they're both representing what that person's individual risk factors are. A couple reasons why this research could end up being useful. The first, of course, is if we were to come up with any kind of behavioral intervention, and that would normally be some kind of psychological intervention that could help prevent future substance addictions. I think the other potential use is in understanding the development of addiction in the first place. So if we understand the time course, so first you get changes in this bit of the brain, that might initiate this sort of behavior, it gives us a much fuller picture over risk and then what could mitigate that risk. So it could be in a follow-up study, some of the people who look high risk in our sample don't go on and develop addiction. And what is special about those people? That's what our kind of neural marker of impulsivity could help us follow up.
It'll be interesting to hear how this develops. Thanks to Camilla Nord from Cambridge University. Earlier, we heard from Amy that drugs of abuse can cause problems with an area of the brain known as the prefrontal cortex. And Edmund Rolls from the Oxford Centre for Computational Neuroscience has been looking at how bits of the prefrontal cortex talk to each other and to other brain areas, and how differences in this communication may be indicative of who might smoke and or drink later in life. Speaking to Chris Smith, this interview was first aired on the eLife podcast in March 2019.
We're very interested in the brain mechanisms of certain sorts of behaviour, including addictive behaviour, in this particular paper, smoking and drinking. And what we have discovered is one part of the brain, the medial orbitofrontal cortex, has different connectivity in people who drink. And the lateral orbitofrontal cortex has different connectivity in those who smoke.
Who did you look at and how?
We studied very large samples of 831 participants in one case from a US project called the Human Connectome Project. And we followed that up with 1,176 participants from London. What we did was to measure the connectivity between different brain regions while people were resting in a brain scanner. We used functional magnetic resonance imaging. What we found is that just when we measured the connectivity between different brain regions, when they weren't doing anything, they weren't smoking or drinking at the time, we found that the connectivity was different in such a way that we could predict, essentially, who later on in life would smoke and who later on in life would drink.
Now, what fraction of the people you studied were smokers and drinkers, and what fraction were not?
The youngest participants were 14 in this study. At that stage, very few of them had started smoking or drinking. They were brain scanned again at the age of 19, and at 19 some of them had started to drink, and we correlated their brain connectivity with their smoking and drinking. The lateral orbitofrontal cortex had low functional connectivity. It was relatively disconnected from other brain regions in smokers. And we think that what smokers were doing were giving themselves nicotine in order to increase the connectivity between brain regions. And we think that that is a basis for that type of semi-addictive behavior, that it makes one more alert because perhaps one's connectivity of the lateral orbitofrontal cortex, but also in fact overall of all brain areas is slightly low in smokers.
So this is like functionally self-medicating, isn't it, to pep up the areas which are underperforming in their nervous system?
That's one of the ideas that resulted from this particular study, that one could consider that that's what happens in smoking. The other interesting thing that happened in this investigation is that associated with the smoking and the underconnectivity of the lateral orbitofrontal cortex, the people were more impulsive. And we think that impulsive behavior is related to low activity in the lateral orbitofrontal cortex. So we think that one thing that may facilitate smoking in people is slight impulsiveness. And that has implications for helping people who may not want to smoke. Perhaps they might understand that if they are a little impulsive, then they should take that into account in their daily routine and to make sure that they're not attracted to cigarettes if that's what they want.
Now, if someone is making up for want of a better phrase, a paucity of functional connectivity between two brain regions, and the nicotine is doing that, when a person who has been an entrenched smoker gives up, what are the consequences for their cognition?
We don't know, but my advice to someone would be if you feel that you need a bit more stimulation, then don't smoke, but take a small amount of nicotine in the form of a pill or a patch, and that might restore your alertness that perhaps previously you sought by smoking.
One would infer from what you're saying that if there is this reduction in connectivity and that the smokers are doing this in order to improve the communication between these disparate brain areas, that if you don't have the nicotine signal there, then there would be a consequence for cognition, either an IQ decrement or an attentional decrement. That would suggest then that if that's manifest at 14, because you're saying that when you looked at the youngest participants who hadn't yet become smokers and they showed similar patterns, do you see underperformance or a tendency towards attentional problems in those young people?
That's not clear yet. The overall point would be that it's possible that those who choose to smoke may have slightly less activation of their brains, and so they may be likely to benefit from stimulation of their brains. But we haven't taken it further than that. What I could say is that we made a second discovery. The same individuals were reporting how much drinking they performed, alcohol drinking. Those individuals had slight over-connectivity of the whole of their brain, and in particular for the medial orbitofrontal cortex. Now that's extremely interesting because the medial orbitofrontal cortex is a part of the brain involved in rewards, in things that one likes. The account we came to, therefore, is that it's possible that those who drink have a particularly sensitive reward system in their medial orbitofrontal cortex, and it's that that attracts them to alcohol. Now, the interesting point here in relation to addiction in general is that we now have two types of addictive behavior which have quite different underlying brain mechanisms. So we should not think that addictive behavior is just a unitary phenomenon. And of course, that's extremely interesting and has important implications for treatment.
Yes, indeed. The other interesting thing about this is, of course, nicotine facilitates communication. It's an excitatory agent, whereas alcohol is a CNS depressant. And if you've got a situation where you have a paucity of connectivity between two brain areas, and that may be being propped up by supplementation with nicotine, and conversely, you've got in people who are wont to use alcohol, you've got an excess of connectivity, then taking something which is a depressant would actually be appropriate under that circumstance.
That would be consistent with the results that we found and reported in the paper. And it is interesting, as you say, that at least in a period of hours, alcohol is a depressant of brain activity. And so it could have the effect of decreasing slightly higher functional connectivity in some individuals.
And what do you think, putting all this together, that the take-home message is? How should cognitive neuroscientists think differently about people who use these agents, and how might doctors and clinicians dealing with people who do approach their subjects differently because of what you found?
I think this has very important implications for understanding addiction in general. There's been an emphasis in the field of the neuroscience research on addiction to think primarily of a chemical called dopamine, which may underlie a lot of addictive behaviour. But if so, that would be a unitary phenomenon, and it probably is important in some sorts of drug, such as cocaine and amphetamine. But here we have two other types of addictive behaviour, smoking and drinking, which can't be accounted for by a simple unitary explanation. There are different things that are happening in different parts of the brain. That then leads us towards potential treatments for different types of addictive behaviour. And the sort of treatment that then could be helpful for those who have smoked is that it may be helpful to suggest a nicotine patch until their brain perhaps normalises its sensitivity a little bit after they haven't smoked for some time. And similarly, for those who may have an oversensitive medial orbitofrontal cortex to rewards, which attracts them to alcohol, then at least some cognitive understanding of what's happening in their brain would help individuals to understand their own behaviour better.
Edmund Rolls there. And that's it for this month. Thank you for joining me on a journey through just a snapshot of the science around addiction. And next month, we'll be moving from substance problems to behavioural ones. England's first ever clinic for treating young people with gaming disorder is opening in London shortly. And gaming disorder has recently been recognised as a mental health issue by the World Health Organization. So join me next time as we hear what it's like to have gaming disorder and what science can do to help. Thank you to Edmund, Camilla Nord, Amy Milton, Helen Keyes and Duncan Astle, who you've heard from in this month's episode. I'm Katie Haler from the Naked Scientist team. Until next time, goodbye.